Hi all, welcome to 12th lecture of this lecture series on Unconstrained Optimization, and today's lecture is on Global Convergence Theorem. But before starting the lecture, let's recall what we did in our previous lecture. So in our previous lecture, we tried to develop an algorithm to solve this minimization problem, in which we try to minimize this function fx such that x takes value from whole of Rn, and f is a continuously differentiable function. So here f is a real valued function, that is f is from Rn to R, that is given. Now the algorithm, we tried various tried to answer various questions and hence developed a algorithm. Let's look at that algorithm that we developed in last lecture. So for unconstrained minimization algorithm, we first initialize the initial value of the variable x naught, some value epsilon which will be used in the stopping condition, and set the iterate to 0. Then we start the loop and we decide the stopping condition where the norm of the gradient is greater than a small value epsilon. So when the norm of the gradient becomes very small, we stop this loop. Then the first step is to find a descent direction. So let's say we are at x naught, we try to find a descent direction. Once we have found a descent direction, we find alpha k, which is the small step length towards dk. And how do we find this small step length? So the step length should be such that the function value on the next point, that is x1, or let's say xk plus 1, should be less than fxk. So that is the requirement. The second requirement is alpha k should satisfy Armio-Wolff condition or Armio-Goldstein condition, which we discussed in the last lecture. Then we update the value, update the variable x, and we also update the iterate. We do this till once the gradient comes under limits, this loop stops, and we set the we find the stationary point x star through this algorithm. Now after we discuss this algorithm, there are a few more questions that are left to be answered. One of them is, what is the guarantee that this algorithm will converge? That is, what is the guarantee that the gradient will come under limits and the loop will stop? What is the guarantee? Is there any guarantee? So we will answer this question in today's class. So with this, let's start with today's lecture. Yeah, so let's try to answer this question. Now consider the problem the minimization of a function minimum of fx where x belonging to whole of Rn. Now there are some assumptions. So let f be a continuously differentiable function and f be bounded below. So this is a reasonable assumption because if a function is not bounded below, then there is no meaning of finding its minima. So it has to be bounded below for this problem to have some solution. So this is a reasonable assumption. Then the second assumption is or second observation you can say is an optimization algorithm is there to minimize fx and it generates a sequence of x's given by xk, correct, and where k is greater than 0. So what an optimization algorithm will do will create, as it goes through the iteration, it create a sequence of variables xk's. That's what this point is saying. And when it is generating a sequence of xk, there will be corresponding sequence of fxk. Corresponding sequence of function values be fxk, or let's call them fk. All right. Now you'll notice one thing, that because we are choosing xk such that we are towards the direction of descent, and you can say that fk plus 1 will always be lesser than fk. So it's not just bounded below, but it is a decreasing sequence of numbers, monotonically decreasing sequence of numbers or real numbers, whatever. And the stopping condition of the algorithm that we saw was the norm of gradient should be less than epsilon. So as soon as the norm of the gradient at a particular point goes below a certain very small value epsilon, the algorithm stops. So if it goes below the epsilon, then the algorithm converges, or you can say it stops. So the question that we asked was, does this always happen? Does this always happen? And if not, then what things should we keep in mind in order to, in the way we choose our descent directions, alpha, step length, etc., so that this converges always. So the question that we want to ask is whether the norm of gk goes to 0 or not, or tends to 0 or not as k increases. So the question is, what happens to norm of gk as k tends to infinity? So as k increases, what happens to gk? Does it goes to 0 or not? If not, what are the things that we should keep in mind so that it goes to 0 and the algorithm converges? So this is the question. So now let every iteration at every iteration the direction d is chosen is a descent direction. Okay, the direction dk is chosen such that gk transpose dk is negative, which means dk is a descent direction. Okay, so the value of fk plus 1 is less than fk. That's what it means. And let's choose the step length. So we define phi alpha as fxk plus alpha dk, and alpha k, which is greater than 0 always, is chosen according to let's say Armijo-Wolf condition. That is the first Armijo condition is fk plus 1 is less than equal to fk plus c1 times alpha dot gk transpose tk, and where c1 is between 0 and 1. Okay, so this is Armijo condition. What was Wolff's condition? Wolff's condition was the derivative of psi at xk should be greater than equal to some c2 times derivative of fxk, and this will be between c1 and 1. C2 belongs to the range C1 and 1. Okay, so these are Armijo and Wolff conditions. So I'll just write it. Armijo and Wolff. So this, as we studied in last lecture, this ensures that there is significant decrement in the function value, and also the step length is large enough. So these two conditions ensure that. So if we take these assumptions into account, we can short say that fk plus 1 is less than fk always for all k greater than equal to 0, and also that xk plus 1 update step is given by xk plus alpha k dk. This is how the xk plus 1 gets updated. Now this condition is given to us. This is true for all k greater than equal to 0, which means fk is a monotonically decreasing sequence, right? And it is also bounded below. What does that mean? So some function which is monotonically decreasing, some sequence, and f is also bounded below. This means that this algorithm, as k tends to infinity, will converge to some f star, right? So fk tends to f star, where f star is less than infinity. So see, it will converge to some value which is less than infinity. Some finite value it will converge to fk, because it is bounded below and it is monotonically decreasing. This also tells us that f naught minus fk is less than infinity for all k greater than equal to 0, and if we apply a limit of k tends to infinity, then also this is finite, because fk is finite, f naught is finite anyways. So the subtraction of two finite numbers is infinite, and it is positive because we know that fk is always less than f naught, right? This is always less, so that is why this is a finite positive number always. This is one relation that we get, which we'll use now. Okay, now using Armijo conditions, alpha j's are chosen such that fk plus 1 is less than equal to fk plus c1 times alpha k dot gk transpose tk. Alright, which can be written as fk plus 1 is less than equal to f naught plus c1 times sigma j equal to 0 to k and alpha j dot gj transpose dot dj. Is this correct? So I just the same relation can be written, this same relation fk plus 1 less than fk plus something can be written for fk. So fk less than fk minus 1 plus something. If I keep on doing that, this will be less than this expression here. I hope it's straightforward, and just if you are still confused, just give it some time to understand why this is true from this expression. Okay, so this we have written. We can now that we have some expression from equation 1, we know what we need to do. We have to just send this on this side and this expression on this side. So let's do that. So we know that f naught minus fk plus 1 then equal to minus c1 dot j equal to 0 to k alpha j dot g j transpose tj, and we know this is less than infinity for all k, right? Correct. So this is true, which helps us say that minus c1 dot sigma j equal to 0 to k alpha j to gj transpose dj is less than equal to infinity. So basically this is a finite sum, and we know that k goes to infinity, can go to infinity. This is true for limit in limit sense also. So this k can go to infinity. Now one thing that you should notice here is that this is a finite value, all right, and a sum of finite values, like so let's say we have a1 plus a2 plus so on and so forth infinity. And if this is a finite number, this is not infinitely small number, all of them are finite numbers, right? This is a finite number, and if this whole sum is less than infinity, what does that mean? Either these terms are negative, the whole of the sum is negative infinity, or if they are all let's first before looking at this analogy, let's look at the signs of these numbers. So we know that c1 is positive, so minus of c1, what will have? C1 belongs to 0 and 1, so this belongs to 0 comma 1, so this will be negative, less than 0, correct? Minus of c1. Now alpha is always positive, please be aware. Alpha is always positive. And what about gj dj? This is negative because we choose dj in such a way that it is a descent direction, and the definition of descent direction is gk transpose dk should be less than 0. So this is less than 0, which means each term of this series is positive, right? So each term of this infinite series is a positive term. Now let's say we have an infinite sum of numbers in which each term is positive, and it is in less than infinity. What can we infer from that? If it is if this sum of finite numbers is finite, then after certain point the terms will start getting to be 0, right? That will happen. I hope it's a logical conclusion. So just think, let's say infinite non-negative numbers are added, a sequence of numbers are added, and their sum is finite. Then after some iterations, or after some sequence, after some terms, the term should be all 0. Otherwise there is no possible way that the term goes to 0, and that the term goes to a finite number, converges to a finite number. So yeah, so we'll use this logical thing. We'll use this logical statement to write that therefore sum of finitely many positive terms is finite. This implies beyond certain iteration, k alpha k gk transpose dk will be equal to 0. So this is one more result. All right. So this we used Armijo condition. Now let's use Bull's condition to get some relation. So using Bull's condition, alpha k is chosen such that how is it chosen? So phi dash of alpha k is greater than or equal to C2 times phi dash of 0, where C2 belongs to C1 comma 1, right? From this we can write let's see what phi dash alpha is. So phi dash alpha is f dash alpha xk plus alpha dk dot dk, which means g of xk plus alpha dk transpose dk. All right. Now this is phi dash alpha. Now phi dash alpha k, what is that? It's g xk plus alpha k dk transpose dk, which in turn is g xk plus 1 transpose dk, which is gk plus 1 transpose dk. Alright. Now what about phi dash 0? It is g of xk transpose dk, which is gk transpose dk. Alright. So let's use these results here. I'll just properly write it so that it's clearly visible. So let's use these results. Right, so phi dash alpha k is gk plus 1 transpose dk greater than or equal to c2 times gk transpose dk. This is the thing. Now what we can do is you can write gk plus 1 minus gk transpose dk c2 times gk c2 minus 1 times gk transpose dk. So we just subtracted gk dk from both sides. That's what we did. Now to proceed further, we'll need one more assumption. Okay, so what is that assumption? Let's look at it. So the assumption is, let G be Lipschitz continuous. So let G be Lipschitz continuous. So what is Lipschitz continuity? So we'll not go in detail about Lipschitz continuous. This will be taught in your in the first real analysis course that you will learn. So we'll just briefly go over it. So Lipschitz continuity means if G is Lipschitz continuous, then there exists a L between 0 and such that gk plus 1 minus gk is less than or equal to some finite constant, positive constant L times the norm of xk plus 1 minus xk. So this is what Lipschitz continuity means. Okay, so this is the definition of Lipschitz continuity. It's a very powerful assumption, but most of the function that we go through the function we'll get the gradient such that they are Lipschitz continuous. Okay, so but we have xk plus 1 is equal to xk plus alpha k dk, right? So xk plus 1 minus xk norm is equal to alpha k. It comes out of the norm because it is always positive, dk, norm of dk. Okay, so we'll put it in this equation, which will give us gk plus 1 minus gk norm is less than or equal to L times alpha k norm of dk. Alright, now which can also be written as, if we multiply both sides by dk, then gk plus 1 minus gk into dk is less than equal to L minus alpha k norm dk transpose dk. Alright, so this is so I'll just mark this as a third condition and this as fourth. Okay, so this is one relation, but by Wolff's condition, like it by 3, by 3 we had that gk plus 1 minus gk transpose dk less than equal to L alpha k greater than equal to C2 minus 1 gk transpose dk. This is was from the Wolff's condition. So what we can write from 4 and 3 is this. Therefore we can write that C2 minus 1 gk transpose dk is less than equal to L times some finite positive number times alpha k times dk dk norm square. Alright, this we can write. So this basically becomes dk norm square. Yeah, so this we can write. Now why is this helpful? So here we can get a limit, like some limit on alpha k. So alpha k is chosen such that C2 minus 1 upon L into gk transpose dk and upon dk norm square. Okay, now if we multiply by gk dk on both sides, let's say alpha gk transpose dk, the inequality sign changes because gk transpose dk is negative. So we'll get C2 minus 1 upon L gk transpose dk whole square because it's a scalar upon dk norm square. So this is inequality sign changes because gk transpose dk is negative. Alright, and now we further multiply by minus C1 alpha k gk transpose dk greater than equal to, because it's minus C1 we have multiplied, so that is a negative number because C1 is always positive, then the inequality sign will change from here, which means C1 times 1 minus C2 divided by L, and we get here, what we get here is gk transpose dk whole square by dk norm square. This is the relation we get, and now let's assume that it's an important assumption, let theta k be the like this is not an assumption, this is just we are giving a name to some value, be the angle between gk and dk. So what will happen is, how can we write this inequality again? So it will be written as minus C1 dot alpha k gk transpose dk greater than equal to C1 1 minus C2 divided by L, and this can be written as gk norm squared dk norm squared cos square theta k upon dk norm squared. So this gets cancelled. All right. But by one, remember by Armio condition we had already proved, but using Armio condition we had already proved that minus C1 sigma j from 0 to infinity alpha j gj transpose dj is less than infinity always. So it is always less than infinity. It's a finite number, and this and then this is one of the term of this series. Please show that. So this term is one of the member of this series, correct? So if we apply the summation on both sides of this inequality and use this relation, we can what do we get? We get C1 1 minus C2 upon L. So this is the constant term, and sigma k equal to 0 to infinity gk norm squared and cos square theta k should be less than 20. This should be finite. Alright, so by using these two inequalities we get this relation. I hope this is logical and understandable. Now this means after certain iteration, this implies after certain iterations k, gk norm squared cos squared theta k tends to 0, right? This is what this means. This we also concluded in when we were using Armijo conditions a little while ago. This is because the sum of this is positive number, you can guess, because this is squared, right? So sum of infinitely many positive finite terms, if it is finite, then after certain iterations the value should go to 0. Okay, that is the thing. So if now, because there are two terms, theta k depends upon the way we choose our descent direction, right? So whatever the direction of descent is, theta k depends on that, and that we choose. So algorithm chooses dk, which we have some control over. So if at every iteration dk is chosen such that gk transpose dk is less than 0 and cos square theta k is greater than some value delta less than equal to, which is greater than 0. So visually it will look like this. Let's say we have some contour map. This is our point of interest. This is and this is our gradient. Gk, this is xk, let's say, and so we choose dk in such a manner that We all know that dk has to be chosen in this side of the area because of for it to be a descent direction. So if we choose such that it is between this area, such that where cos square theta k is greater than some value delta, then we can ensure that, because now cos square theta k never goes to 0, right? It is always greater than some value delta. Then we can ensure that limit of k tending to infinity gk equal to 0. So gk has to go to 0, given that cos square theta k is never close to 0, it is always finite, and because their product goes to 0, then the gk norm has to go to 0. So this proves that if we you choose descent dk such that it is a descent direction, we choose alpha k by Armijo and Wolff's condition. The gradient g is Lipschitz constant, Lipschitz continuous, and we choose dk such that cos square dk theta k is greater than some value delta, then this ensures the algorithm will converge. Alright, so convergence is guaranteed. And this actually is called Global Convergence Theorem, which we'll state now. Okay, so what is Global Convergence Theorem? The same idea that I explained it to you a little while ago, I'll state it in words. So what I'll do is, as I always do, I'll just write the theorem first and then I'll explain it to you. So consider the problem to minimize fx over Rn. Suppose f is bounded below. These are all the assumptions that we assumed earlier. Suppose f is bounded below. Below in Rn. And f is continuously differentiable. And one more important assumption was the gradient is Lipschitz continuous. These are some assumptions. Now, if at every iteration of optimization algorithm a direction dk is chosen such that cos square theta k is greater than delta, which is itself greater than 0. So cos square theta k, we always choose dk such that this angle between dk and gradient, its cosine square is greater than some positive value delta, where theta k is angle between gk and dk, and alpha k satisfies Armyho-Wilks condition. Then the optimization algorithm either terminates in finite step. Night steps or limit of k tending to infinity gk norm goes to 0. Okay, so this is the global convergence theorem, that if certain assumptions are followed, that is bounded below f is distributively continuous, gradient is Lipschitz continuous, and theta k is chosen such that it's cos square theta k is greater than some value delta, and alpha k satisfies Armyho-Wilks condition, then the optimization algorithm either terminates in finite steps or the gradient goes to 0, which means eventually it will converge. So that's the idea of global convergence theorem. So here we have proven that the algorithm that we discussed earlier, which had all these assumptions in place, will converge. So with that, we'll now move to other topics. So we'll start with sufficient degrees and backtracking. Yes, so now let's look at like the backtracking algorithm. So what is backtracking algorithm? So we already know that we choose step length according to Armyho or Wolf, Armyho and Goldstein, or Armyho and Wolf condition. But let's look at an algorithmic form in which we can choose the step length, and that is called backtracking. So let's look at what backtracking is. Okay, so let's relook at what is Armyho and Wolf's conditions, Armyho Goldstein condition. Okay, now which means choose alpha k such that f xk plus alpha k dk is less than or equal to phi 1 alpha k and is greater than or equal to phi 2 alpha k, where phi 1 alpha k is given by fk or fxk plus c1 times alpha k dk and C1 belongs to 0 and 1. It is a number between 0 and 1. And phi 2 alpha k is fxk plus c2 dot alpha k dot dk, where c2 belongs to c1 and 1. Okay, so this one is Armijo condition, and this one is Goldstein. Okay, and to get there, they ensure that the step length that is being chosen has a significant value, and also the reduction in the function value is also significant and helps in convergence of the algorithm. Now let's look at backtracking algorithm, how you can use these conditions in an algorithmic form, which is called backtracking. So use of backtracking line search with Armijo's condition. Alright, so backtracking line search. Let's write the algorithm. So first step is choose some initial value of alpha hat, which should be greater than 0. Choose a constant row between 0 and 1. We'll see what is its usage. Select some constant c1 from 0 to 1 and set alpha is equal to this alpha hat, this the initial value of alpha. Okay, so this is the first step, basically initialization step. Then we run a loop while fxk plus alpha k dk is greater than fxk plus c1 dot alpha dot gk dk transpose dk. Basically this means that till Armijo condition is not satisfied, we keep on updating alpha such that it is being reduced. So if this is between 0 and 1, so row alpha actually decreases the value of alpha. So we keep on updating alpha till Armijo condition satisfied. Once it's satisfied, we end the loop. And output is given as alpha k equal to alpha. So basically the stopping condition is Armijo conditions. If it is not satisfied, we keep on reducing the value of alpha. Once it satisfies Armijo condition, we come out of the loop and we use this step length. So this is a generic algorithm. You can modify this algorithm to support both Armijo and Goldstein, or maybe Armijo and Wolff's condition also. It will be a small modification. So let's say if it satisfies Armijo and doesn't satisfy Goldstein, you increase the value of alpha. If vice versa, then you decrease, and if it satisfies both, you end the loop and come out. That can be a modification that supports both Armijo and Goldstein. So this is how you can find a step length which ensures convergence by selecting the step length according to Armijo and Goldstein condition. Okay, That's that. Now let's move on to the question how to select the descent direction. So till now we have selected, we know how, like, where the descent directions come from, but how do they get, like, so how do we choose descent directions? So let's just quickly recall what descent direction is visually. So let's say this is the contour map of a function, and contour map of a function, let this be the point xk, and this be the gradient of the function at this point, that is gxk or gk. So if our algorithm is currently at this point, what would be the possible descent directions? It turns out, as we know, that descent direction are such that the gk transpose dk should be less than 0, which means all the descent directions should make an obtuse angle with the gradient, which means all the directions in this region are descent directions. So basically, if I choose anything from here, this is one possible descent direction. Okay, so what is a descent direction set based on this? So descent direction set it is a set of all the possible values of all the possible directions that can be a descent direction at the given point. So D belonging to Rn such that gk transpose dk is less than 0. Okay, where we know that gk is gradient of fxk, right? So this is the meaning of what descent direction is. Now how can we choose descent direction? So out of the so many descent directions which belong to this set, which descent direction should we choose? How should we go about choosing our descent direction? So let's look at that. So topic is descent direction. Okay, so let at a current point the gradient should not be equal to 0. So because if there is the gradient is 0, we are actually at a stationary point. So, and at that point we cannot depend upon gk to find the descent direction. So let's assume this, that gk is not equal to 0. Then and the descent direction be given by some ak gk, some ak times gk. So ak is a matrix where ak is a symmetric matrix. So how can we say that this is a so let's look at what this ak is doing to, when we multiply ak by gk, what is exactly happening. So let me just take this diagram with me. All right, so okay, so this is the diagram that we were talking about. This red spanning area tells us this is where descent direction we can choose. So what dk equal to ak gk minus ak gk where AK is symmetric, tells us. So it can be written as AK times minus GK. And what is this minus GK? So minus GK is opposite vector to GK, right? This is minus GK, right? Now AK is being a symmetric matrix, just gives the rotation of GK, rotation of minus GK. So we just rotate this around, we rotate this vector around with AK. We choose AK such that we can rotate this GK around such that it remains in this red spanning region, but so that it's still a descent direction. So that's what AK is doing. Now let's assume that if AK is positive definite, then what happens? So we know that it is symmetric. What if it is positive definite? Okay, so let's look at the dot product GK transpose DK, which becomes minus GK transpose AK GK. And because AK is positive definite, this value is always positive, right? This boxed element, and we apply a negative sign, then whole becomes negative. So this whole thing is always negative, which means this is always negative, and DK is a descent direction. Which means if DK is given by minus AK GK and AK is positive definite. So if AK is positive definite and DK is given minus AK GK, then DK is a descent direction. Okay, now so the thing is, different optimization algorithm use different values of different AKs according to their theory, that what should AK be so that the algorithm is faster, or like it follows some property. So how do we find this DK, or in turn AK? Let's answer that question. How to find DK? So find DK, or now that we have given it a structure, minus AK GK, how to find AK? All right. So how do we find that? So in one of the methods, we approximate our function. So consider the first order approximation to fx about xk. So what we do is this is xk, and let's say this is contour maps. We take the first order approximation of fx around xk. Okay, so how do we, what is the first order approximation? F hat x defined by fxk plus is equal to let's assume that x minus xk is some value d. Okay, so this is the linear approximation. Here, this d is the direction. So let's say this is xk, and this is the direction d in which we choose our next point. This is, let's say, x. So x minus xk, x is equal to actually given by xk plus some alpha times d, right? So x minus dk. We assume that this is some vector d which includes the step length magnitude in itself as well. So that's what uh, we are assuming here. So d is basically direction plus magnitude. Now it is important to note that what we want is max decrease in decrease in f hat x. So we want to find a d such that there is a maximum decrement in f hat x. So it is possible by solving the following optimization problem. So following optimization problem, what is a optimization problem? Minimize over d gk transpose d. So d is the variable such that d transpose d equal to 1. So why is this constraint here? Why is this coming here? So what it means is we want to find a direction, and magnitude doesn't matter actually. So magnitude we'll find later. We want to find a direction in which if we move, we get the maximum decrease in fxk. So we can assume that the magnitude of the direction is 1, magnitude of d. So we want to find the best direction, so we are removing the step length away. So you can see, so basically you can understand this, that gk transpose d will be negative, and if we want to find the minimum value of this, which when added to fxk will result in the maximum decrease in f hat x. So that's what we want to find. So how do we go about solving this problem? So let theta k be the angle between gk and d, implies gk transpose d is given by norm of gk norm of d cos theta k. Now because d has unit magnitude, gk norm cos theta k is the value. We want to find the least value of this. We want to find the least value of this function now. Now gk is fixed for a given xk, right? What is the least value? It depends only on theta k. So what is the least value of a cosine function? It's -1, right? And for theta k equal to pi, right? Which means d is in opposite direction to, like, opposite direction of dk, right? So solution to this problem, so I'll just let me show you visually. So this is the gradient, and the 180-degree thing is, so, and dk is the, this is, let's say, d, and this is gk, and theta k is this angle. So for maximum decrease, this has to be pi, which means in this direction, right? So I hope this visually it is understandable. The solution to this problem is d equal to minus gk upon gk norm, because d is unit norm, so it is this. So basically this is if we assume the function to be a linear, if we approximate it linearly, then the maximum decrease will happen when the direction in which we descend is the opposite direction of the gradient, and this is called, this method is called steepest descent direction. Steepest descent direction, and in this direction AK, what will be AK? AK will be identity. Okay, so this is one of the algorithm called steepest descent algorithm, which we'll discuss next. Now let's discuss the steepest descent algorithm. Steepest descent method. So here we'll use steepest descent direction, which is given by, as we saw earlier, tk is equal to minus gk. Okay, so let's write it in algorithmic form. Steepest descent algorithm. The first step is initialization step, in which we initialize the x, epsilon, etc. So we initialize x naught, epsilon for use for stopping condition, and set the iteration variable k. The second step is the actual loop. So while stopping condition is satisfied, that is gradient of the norm of the gradient is greater than epsilon. If this is true, it will keep on running the loop. And then the first step is the important step, in which we select the descent direction. So what is the descent direction this time? Minus gk. This is basically the main algorithmic step, that is selecting the steepest descent direction. In the next step, we have to choose the the step length. So find alpha k greater than zeros along dk, such that first thing is that the function value should reduce, should be less than fxk. And second is the Armijo and Wolf condition should be satisfied, or Armijo and Goldstein. Armijo alpha k satisfies Armijo and Wolf conditions. Oh, all right. Now comes the update steps. So we just update the xk. Alpha k dk, and we also update the iterate. Here we end the loop. Just fix the indentation. Yeah. So this is how the loop works. So we first initialize loop, we run the loop in which we first select the dk according to steepest descent direction, and then choose alpha k through Armijo Wolf condition, and that's it. Now we send output. So output is nothing but x star equal to xk, which is the stationary point of fx. So this is the algorithm in a nutshell. Now one more thing is that we also saw the backtracking algorithm, right, which was used in Armijo. So here in this step you can use backtracking line search or exact line search, whatever you think is whatever you want to do. So exact line search has a computational problem, but backtracking it does not have that, so you can do either one of that. So exact or backtracking line search can be used in step 2b. Alright, so this is the steepest descent algorithm. Now let's look at some examples which use steepest descent direction. So example 1. So here we want to minimize a function fx, which is defined as x1 minus 7 whole square plus x2 minus 2 whole square. So just by looking at the equation, you can see that it's this equation will have circular contours. So let's draw the contour map. Alright, so this is the contour map. Let me draw it again. So this is the contour map. This is y-axis. This is x-axis. And now let's draw a circle. So this will have a circular contours. It's easy to see that. Okay, so circular contours. So now let's look at the gradient of the function. So what is the gradient of the function? It's 2x1 minus 7 and 2 into x2 minus 2. This is the gradient vector. And let's look at the Hessian. So because it's a quadratic function, Hessian will be constant. All right. And this point, this point, what is this point? This is actually 7, 2. The contours will be centered at 7, 2, and this is exactly actually the optimal point as well. So x star is equal to 7, 2. All right. Now let's say we start with some point here. Okay, let's say this is for steepest descent algorithm, this is x0. So it turns out if we follow the steepest descent direction, it will go to the minimum point in just one iteration. Now if we take some other point, let's say some other point, it will again go to the optimal point in just single step. If you use steepest descent method or algorithm. So let's report this observation. So behavior of steepest descent direction algorithm with exact line search. So here we are using exact line search. Applied with two different points. Two different initial points, took us to the minimum in just one step. And this happens actually because of circular contours. Alright, so this happens because of the circular contour. So let's say you have a quadratic function like this, which has circular contours. So if you apply steepest descent direction and you take any initial point and use exact line search, you will reach the optimal point within one step, whichever initial point you take. And this happens because of circular contours. Now let us look at some quadratic functions with non-circular contours. Okay, let's look at them. So let's look at example 2. So minimization of fx defined as 4x1 square plus x2 square minus 2x1 x2. Okay, so let's draw the contour map of this. So this is the contour map. Let's say this is the y-axis, this is the x-axis, and it turns out the contour map of this function will be something like this, elliptical. Let me try it properly. It will be elliptical like this. Now let me So this is how the contours will be for the for this function. Let me bring it to the center. So now if we apply steepest descent direction in this, let's see what happens. So first of all, let's write what is the gradient for this. The gradient will be 8x1 minus 2x2 and 2x2 minus 2x1. This will be the gradient of the function. Alright, what is the Hessian? Again, this is a quadratic function, so it will be a constant matrix, and it will be my 8 minus 2 minus 2 and 8. Alright, and it turns out the optimal value happens at origin 0, 0. Alright, so this is the thing. Now if you, so let's say we take this as an initial point. Okay, and this here is the optimal point here. This is here is the optimal point somewhere here. Okay, so if we apply the steepest descent direction, what happens? It turns out that it forms a zigzag shape curve. So like this is the first step that it will go. Second step, third step, fourth step, fifth step, sixth step, seventh step, and it will take a lot of steps from this initial point. A lot of steps along this initial point, and it turns out if we take some other initial point, let's say this one, it goes to the optimal point in only 4 steps. So this is the change. So here the number of iterations is dependent upon the initial point in steepest descent direction. Here this happens because this is a non-circular contours. So let's state our observation, that is steepest descent takes a lot of steps for one initial point and only 4 steps for another. So why is this? Why does this happen? So the answer to this question we'll try to give it in the next lecture, where we'll go deeper into the steepest descent direction algorithm, and we also try to analyze it much better so that we know everything about steepest descent direction. So we will end the lecture now and we'll be back in the next lecture. Thanks.